So atoms, ions, and molecules, the building blocks of matter. And here's what our learning goals are. As usual, we start out with this. Be able to explain how major scientific experiments contribute to our understanding of atomic structure. Write chemical symbols and equations describing subatomic particles. Explain and predict properties of elements using the periodic table. Interconvert mass, moles, molar mass, and number of particles. That's the bulk of the calculations here. Like I said, we'll do an isotopic abundance calculation too. It's going to be tough, but that's the rest of it. So the beginning stuff is qualitative, and the end stuff is more quantitative. J.J. Thomson, without a P, 1897. So he sets up this experiments with these cathode ray tubes. And basically what that means is he's got this power source, this high voltage power source, and this cathode is just a piece of metal. Okay, and you can use different metals. Okay, anything that's going to conduct electricity. Okay, and what he noticed with both magnets and positive and negatively charged plates, and then he had this kind of phosphorescent screen back here. This is not much different than an X-ray, the way an X-ray works, right? You've got energy exposing a film, or so I grew up taking, I'm a big photographer, and I grew up taking film and developing my own pictures too. We all use digital now, of course. There's still some holdouts on that, but same type of thing, right? You got light exposing a particular material that's light sensitive, and that gives you your image. So no different here. He's got this coating here. What he notices is that these particles are deflected. Okay, they don't just pass straight through, which means they have an attraction. In this case, you can see it's towards the positive plate. And it's also deflected in a magnetic field. So it means the particle has charge. And what he noticed was it didn't matter what the metal was made of or what the cathode was made of. He got the same effect. And he got a constant mass to charge ratio, which means if the charge increased, the mass increased proportionally. It always had the same ratio. Okay? So from this, he was concluding that basically there must be this fundamental particle that's part of matter. And it has a charge, a negative charge. I mean, you have to, flash back to the time period and realize that they thought that matter was basically like billiard balls, just solid, no other different substance making it up, if you will, just kind of uniform, solid thing. That's it. So to see something like this to them was shocking. So what Millikan does, he comes along to try to, elaborate on this experiment and do something different. Now, keep in mind, at this time, we know all of the laws of physics. We know electricity, we know magnetism, we know gravity and attraction, Newton's laws, the particles, any two particles in the universe attract each other. Okay, that's one of Newton's laws. You're attracted to the moon. Okay, that attraction might be small, but you are attracted to the moon based on your masses. Okay, so what he does, he takes these oil droplets and atomizes them. All that means is he creates a fine mist. Okay, really small particles. It doesn't mean they're single atoms. Okay, you're atomizing, it's creating these very small particles. And of course, they will settle under the force of gravity. Okay, and what he does is a brilliant experiment. I love this experiment. If you have a favorite experiment, this is definitely up there. If you're ranking experiments. All right, so he atomizes it, and then what he does, he hits them. Where is it? Oh, there's my X-ray source there. He hits them with some X-rays. And X-rays are what we call ionizing. Okay, so there's certain energy that's ionizing. That means it's energetic enough to dislodge electrons. And that's what makes it dangerous. That's why you're only allowed to be exposed to certain amounts of X-rays, right? That's why when you go to the dentist, they put the lead blanket on you, right? Gotta forget that I can't do stuff like this because my image flips on me. That's why they cover you with a lead blanket, right? Now, some of the new dentists, I went to one that did this a while ago where they're just standing you up now and the machine just goes like this around you. You don't have to wear a lead blanket or anything. That's why if you're pregnant, you don't want to get X-rays because this energy can be dangerous, and that is because it dislodges electrons. So what's happening here is he's ionizing the air molecules, and then the electrons will adhere to those oil droplets, okay? And then what he does, he has these charged plates. And it's falling under the force of gravity, right? And we can calculate that. We know from Newton's laws, right? Based on acceleration due to gravity, G equals 9.8 meters per second squared, we could figure out how long it should take to there or what rate it's falling at, right? So he controls the electrical field to get the particles to be attracted to the positive plate, slows down their drop, and he can figure out the charge based on some electromagnetic equations, okay? Because we know what rate it should fall, and he knows what amount of charge he's using or voltage he's using, so he can figure out what the charge is on that particle, because that will determine how fast it falls. And since we already knew this was constant, he was able to calculate the mass to charge ratio and the charge on the electron. And of course, if you know the mass to charge ratio and you know the charge, you can now calculate the mass. So that's what he did. Whoops. That's what he did. So he got the mass and the charge of this fundamental particle, which we now call the electron. We know it's negatively charged. We know its mass, and we know its charge. You can see, obviously, the mass is very small, 10 to minus 31 kilograms. Those are numbers you can't even fathom. 10 to the 9 is a billion, right? We're talking 10 to the minus 31. When my son was real small, I wanted to convince him how big the number of billion was, and I had him count to like 100 and timed it. And then I told him, okay, it would take you, 10 years to count to a billion, just to demonstrate how big that number is. That's counting pretty fast, actually. If you can keep it up for that long, more likely it's going to take you double that time. But anyway, you get the idea. This is a huge or really small number. That's a huge exponent or a super small exponent, 10 to minus 31 kilograms. All right, so now we know that matter's neutral because we know matter has no charge. Okay, so if I take a sample of sulfur, nothing happens to an electric field, right? So we know it's neutral. So even though we haven't discovered a proton, we know there must be a positive particle somewhere to equal out the negative particle. Without having discovered it, we know that. Later on, the proton was discovered. So Thomson now, the same Thomson right here, discovered the electron, comes up with this plum pudding model. Now, I've never had plum pudding. So if you've had plum pudding, maybe you can relate to this more. But basically, he saw this as a swirl of positive and negative, basically. Okay? Electrons embedded in this positive, swirling sphere or whatever. Okay? So that's the idea. So Rutherford comes along. Incidentally, Rutherford was a Nobel Prize winner. So before Rutherford, though, I need to tell you that Marie Curie, one of my all-time favorite scientists, brilliant woman, won 2 Nobel Prizes, chemistry and physics. At the time of her PhD dissertation came out, they said it was the most profound work in that field to date. I mean, she was just an incredible woman. She gave her life for science. She basically wound up dying of leukemia. She worked with radioactive materials back when we didn't know what kind of damage they did. They started to figure it out themselves as they got sick. She used to work in like a, little shacky warehouse that they converted and stuff like that, and getting loads of this material, uranium and polonium, things like this. So what they realized was that, so this was somewhat serendipitous the way he figured this out. So basically, in his lab, he had some photographic film, okay, like an X-ray that was unexposed, you know, or kind of like photography film, kept in the dark, right? And I guess one of the persons working in the lab had some of this uranium, and he put it in the same drawer on top of the, you know, the film. So Burquell goes in to get the film out, and he realizes it's exposed. So, well, you know, someone must have shined light on it and exposed it accidentally. So he put new film in there, and it happened multiple times. We started to suspect, wait a second, what's this here right here? Why is this, what's going on here? We started to realize it and tested it after it came up with the hypothesis that the uranium was exposing the film. So uranium is radioactive, and it gives off energetic rays that are both ionizing and then will expose a film. So this is what radioactivity is effectively. It's the spontaneous disintegration of a nucleus. Okay, spontaneous in the sense that we can't control it. We don't have any power over it, if you will, for lack of better words. The nucleus is unstable in certain elements, and in an attempt to stabilize itself, it gives off energy and particles until it can stabilize itself, in a sense. No, I'm talking like a conscious person. Obviously, the nucleus is not conscious. Says, "Oh, I'm unstable. I need to get rid of some of this stuff." It's just a random, spontaneous process. Not much different than like if, well, I don't know if I come up with a good analogy. Yeah, I can't come up with a good analogy right now. But spontaneously is giving off energy and particles in an attempt to reach a stable state. Okay. So I always tell my students in general chemistry, what drives everything in nature is moving towards a greater state of stability. Okay. Chemical reactions. Why does this chemical reaction happen? Why does this one not happen? Well, this one happens because the products are more stable than the reactants. This one doesn't happen because the products are less stable than the reactants. This radioactive process for certain elements happens because it's unstable, and ultimately it's going to reach a stable state as it goes through this process. So it gives off alpha and beta particles and gamma rays in an attempt to give off energy to stabilize. Okay? So if something is a high energy state, it gives off energy until it kind of gets to a more stable state. So basically, knowing this, Rutherford comes up with the idea now that he can take radioactive materials like uranium, and it's going to give off alpha particles. Now, for the sake right now, I'll tell you an alpha particle is equivalent to 2 protons and 2 neutrons. Okay, for right now, that's all you need to know. It's equivalent to 2 protons and 2 neutrons. So what he does, there's his screen again, and he's going on this hypothesis right here. He's saying, okay, if this is the correct model of the atom, then when these beta alpha particles, which are going to come out, he's got a hole here. This is like a lead block. He's got a little hole over here. So the alpha particles can only go straight out the foil like this. He uses gold because he can pound it into a really thin sheet. And there's a calculation somewhere either in the back of the book or smart work. I don't know if I signed it. Where you actually calculate how thick Rutherford's gold foil is. And I forget what the answer is, but it's still like 10,000 atoms thick, something like that, which is really small, really thin. So his idea is, okay, well, this is an alpha particle. So it's 2 protons and 2 neutrons. And it's moving at a pretty good speed. You can Google that. I forget what the speed of alpha particle is, but you can Google it. What's going to happen if he shoots an alpha particle at an atom that looks like this, or if you will, keep in mind it's a gold foil, so it's going to be a bunch of atoms like this, and in 3 dimensions, so this is 2 dimensions, and then, here and then in back. What's going to happen if he shoots an alpha particle like that? Knock off electrons, bounce off. Like what? Bowling's a better analogy than the other 2 things that were said. So I'll give you even a better analogy. Andrew's going to take a shotgun, and I'm going to hold a piece of tissue paper up here. And he's going to fire the shotgun at the tissue paper. You all know what's going to happen, right? That's what should happen, because keep in mind, that electron is, and I didn't tell you this, mass-wise, much less than a proton or a neutron. It's like 2,000 times less. And not only that, an alpha particle is 2 protons and 2 neutrons. Okay? Shot at a high speed at this thing. Now, keep in mind, it's a lot of space here, right? Okay, so his prediction was that most of the particles, his hypothesis, should go straight through. Maybe occasionally getting a slight deflection as it hits off an electron. But that would be rare because the atom's mostly space here. And that's in fact what he saw for most of the time. But then he saw this occasionally. And that's like that occasionally Andrew's shooting at my tissue paper, and one of these bullets come flying back towards him. This was groundbreaking. Never predicted this. And the conclusion is, well, wait a second. For that bullet to be coming flying past me once in, I think it was something like once every 8,000 alpha particles. 1 in every 8,000. I would have to conclude that in that tissue paper, there must be something pretty massive, right? That's causing that bullet to fly back in. So that's the conclusion he comes to, is that in fact, there must be some small, massive center to those gold atoms in order for this to happen. Something much more massive than the alpha particle. So he now comes up with the idea that, hey, we've got those positively charged particles, which haven't even been discovered yet, and we haven't discovered neutrons yet either. But the idea that there's mass in the center of the atom. Well, not the center, but there's mass somewhere in the atom. Okay? Now we have an idea that's, structured in the center of the atom, the nucleus with the orbits around it. We'll talk about that and come to the planetary model. But there's still, at this point, the electrons are still diffusely spread throughout. But now we have this massive center. Does that make sense? Questions? Yeah, so that's an excellent question. The nucleus is so dense that, and it comes from the fact that it's so incredibly small, but the nucleus is so dense that it's compared to the density of like a collapsed neutron star, which they tell you that if you had like a teaspoonful of it would weigh something like 2 billion tons. Don't quote me on that, but it's something astronomical like that. You can't even conceive of the density. That material is so dense, and the nucleus is so dense because it's an incredibly small volume that these protons and neutrons we now know are packed into. So that's an excellent question. Yeah, super dense, the nucleus. But super small, and that's why he only saw a few of these really blatant bounce back deflections. Other questions? So to finish up today, let's just say that the new atomic model assumed that there was a very tiny positively charged nucleus that contained like nearly all the mass of the atom. And now we know, I think it was 1932 with the neutron, Chadwick, I believe it was. And the proton was discovered by Rutherford also. I want to say, let's see, what year was this experiment? One of them's 1919. I don't know if it's the proton discovered or Rutherford's experiment here. That's just 1932, not 1982. It looked like an 8 for a second. All right. So here you see, there's where I show you the masses. Now look at the mass of the electron, and that's in atomic mass units. You can look over here to kilograms, 10 to minus 27, 10 to minus 31. That's almost 10 times 10 to minus 31. So that would be 1 times 10 to minus 30, then, if you will. That's still a factor of 3 there, right? 30 and 27. So it's a pretty huge difference. And there's the actual charges. Those are coulombic charges. That C is a coulombs of physics units of charge. But there's our relative charges. And if you will, kind of relative masses based on atomic mass units. And that's just a normalized scale atomic mass units. We'll talk about that in more detail when we talk about the periodic table. That's a good place to stop. So you're ready for your quiz now. Of course, the quiz can have more than what we covered, of course. Just follow your outline, things like isotopes and stuff like that.